In this class, we will discuss about the design of beams or the behavior of beams, behavior of cold form steel sections in bending. So we have learned how to design beams using hot rolled sections, ISLB, ISHP, ISLB sections. Now in this class, we will discuss about how a cold form steel section can be used in the design of beams. So here we will see the basic concepts which is used in the design of beams using CFS. So one important stress value we have to compute here, that is called as the maximum compressive stress value acting on the beam element, which is given by this formula. P naught is equal to 1.13 minus 0.0019 into d by t into root of fy by 280 into py, and this value should not be greater than or equal to fy, or it should be less than fy. So that's what the codal provision says. Here the nomenclature is like this: d by t is nothing but the ratio of depth to the thickness. Suppose if this is the section which is used as an example, I will take. So this is section which is used. Now here this is your d, depth of it, and t is the thickness of it. So this d by t ratio. Then fy is the yield stress value. Normally in the case of cold form sections, steel sections, the fy value varies from, you know that it varies from 230 to 280 Newton per millimeter square or MPa. And Py is called as the design strength. This Py is called as the design strength, which is also expressed in MPa. So here one condition which says that for steel with Fy is equal to 280 Newton per mm square, suppose if this is 280, then this becomes 1. This P naught should be taken as equal to Fy. So P naught should be equal to Fy, provided the depth to thickness of the web ratio is less than or equal to 68. Less than or equal to 68. So this is one special condition as given in the code. And in the case of members subjected to bending, we need to calculate an important parameter called M ultimate. So this M ULT is nothing but the ultimate moment capacity of the section, which is normally expressed in a Newton millimeter or kilonewton meter. For that we need to compute the value of Zc, which is called as the effective compression section modulus, which is expressed in millimeter cube or centimeter cube. So when this effective section modulus is multiplied by this whatever compressive stress, maximum compressive stress value P naught is there, we are going to get the value of ultimate moment capacity of the section. You can just observe that this is similar to your pure bending of beam, which are studying strength of materials. So section modulus multiplied by the stress will give the moment carrying capacity in that case. So similar to that, you have here M ultimate is equal to Zc into P naught. Now in the code he has given the maximum or the limiting. So maximum can also be written as limiting values of width to thickness ratios as for the bending elements he has given in the code. So if it is a stiffened element, it should be less than or equal to 25 into root of 280 by Fy. If it is an unstiffened element, it should be less than or equal to 8 into root of 280 by Fy. So this is the limiting value or the maximum value of width to thickness ratio for a bending element in a cold form steel section. Now when you are designing a beam using a cold form steel section, we had to first learn what are the different types of failures that may occur. So there are two main important failure criteria in the case of CFS section subjected to bending. One is the wet crushing, another one is the shear buckling. So one failure may be due to crushing, another may be due to buckling. So normally this crushing occurs in the case of what you can say shorter web sections. So web crushing will take place like this. So here this is the supporting beam. So this beam is the supporting beam. On this beam another beam is running like this, perpendicular to that. So the web crushing will occur like this. So the web will crush like this, it takes a shape like this. So this can occur, web crushing can occur under concentrated loads or reactions at supports when deep tender webs are used. So when deep tender webs are there, then this web crushing may occur and it may take in this fashion. To avoid that web crushing, so you can always provide a web pleat at the support points. So to support this section, like this, something like this. When arrangement is provided like this, then you can avoid this web crushing. The second type of failure in beams is the shear buckling, which can occur in thin webs. Once again, thin webs means slender webs, you can say. So this is how the web shear buckling will occur. So this is the section. So this is the along the length it is shown like this. When it is subjected to load like this, so load is applied like this. When it is subjected to load like this, W. So buckling of this web takes place, and due to that, you can see some perforations like this in the web region. So this is the web region. This is the web. So web buckling may take place due to the development of excess amount of shear. So the condition is the maximum shear that is going to develop should be less than or equal to 0.7 times Fy value, and the average shear stress PV should be less than or equal to 1000 T by D whole square. So when the value of shear stress exceeds this, then this type of failure may happen. Now the third one is the lateral buckling. So this lateral buckling concept you have learnt in unrestrained beams. So where this can happen in the case of long beams with low lateral stiffness and low lateral torsional stiffness. So stiffness can be in any way. It can be axial stiffness, it can be bending stiffness, or it can be torsional stiffness. So when it has got low bending stiffness and torsional stiffness, then this lateral buckling may take place. So in that case, the effective length of the beam, in such a case, the effective length of the beam plays an important role, which depends on the support condition as well as the loading conditions. Now this is how a beam may be subjected to lateral buckling like this. So this is along the length of the beam. So it is subjected to this section is subjected to both bending as well as twisting. So this I have explained in the unrestrained beams. You can refer to that video. So here both bending effect also will be there and twisting effect also will be there. And that means in plane effect also will be there, out of the plane effect also will be there, and the section will take a shape like this. This I section is an I section. I section will take a shape like this. So when it is simply supported. So this is this is a sketch which depicts the effect of lateral buckling, which consists of both bending and twisting in an I section. Also symmetrical, you can say. And when the load is acting along the shear center, you can expect this type of failure. And in this case, we have to compute one important value of moment called ME, elastic lateral buckling moment capacity of that section, which is given by this formula. Once again, this formula is there in the code. You can just, you should know the nomenclature of this. So ME is the elastic lateral buckling moment capacity. So A is the cross-sectional area of that particular section, which is used as the beam. E is the Young's modulus of steel, and D is the depth of web in millimeters. T is the thickness of web in millimeters. Ry is the radius of gyration about the y axis in millimeters. Le, of course, is the effective length of the beam in millimeters. And here CB. This CB is one important parameter which is given by this expression 1.75 minus 1.05 beta plus 0.3 beta square, which should be less than or equal to 2.3, where this beta is always less than or equal to 1. It is the ratio of, beta is the ratio of the smaller moment to the larger moment which acts at the ends of the beam. Okay. So in the case of beam columns also we are using this concept. There we are calling it as psi. Here it is beta. So suppose if this is more, if this is more, beta will be this divided by this. Okay, so suppose this is m1, I will take this as m1, this as m2. Let us say they are of different magnitude, then beta will be given by m2 by m1. So beta is equal to m2 by m1. And the deflection may be in two ways. One is called as the single curvature type of deflection, another one is called as the double curvature type. So it is like this. In case of single curvature, the moments will be having opposite nature. In the case of double curvature, they will be having the same nature, either it is clockwise or anti-clockwise. Here one is clockwise, another is anti-clockwise like that. So anyway, the value of beta is always less than or equal to 1. So depending on the value of beta, so we have to simplify and get the value of CB, which should be less than or equal to 2.3. That means if it is less than 2.3, we have to take that value. So that is the meaning. If it is greater than 2.3, we have to restrict it to 2.3. That is the meaning of that. So once you substitute those values in this expression, you are going to calculate this value of elastic lateral buckling moment capacity of that particular section in bending.